Okay, hi linear algebra. This is your solution screencast and my explanation. The first thing though, Severin. Remember when I was looking at your calculator and I turned your apps off? To get to the matrix input screen, you have to hit apps and then you won't see the app symbols, but you'll see a list. When you hit apps, number 6 will say like data slash something slash matrix. Go to number 6, hit the right arrow and choose matrix. Okay. Severin, did you hear that? Okay, that was for you, Severin, because Severin didn't have his apps turned off. If you had your apps turned on, like Heather, you will have the picture of the apps, but I like having the apps turned off. Okay. All right. Here is your solutions worked out. It is about 1:30 right now, so I have done 8 of these. Okay, question number 1 and my explanation are right here. You can read it. Again, like I said in class, I treat reviews as more like a thorough studying, so I like to be thorough. A 2 by 4 augmented cannot yield a unique solution because a 3 variable system needs at least 3 equations to determine a unique solution. In this 2 by 4, we only have 2 3 variable linear equations, and their intersection will either be in a line, infinite solutions, or they'll be identical planes if they're infinite solutions again, or it'll be non-existent in the event that these 2 planes are parallel. Okay? All right. A 5 by 4 augmented represents 5 3 variable linear equations. I wrote, if no row is a multiple of another, there is a possible unique solution, in which case the 5 planes intersect in a point, or there are infinite solutions, 5 planes intersecting in a line. Okay. Question number 3 about the homogeneous system. If you have a homogeneous system, 3 equations and 3 unknowns, that means that the right-hand column is 0. They're all zeros. Possible solution sets are the unique solution 0, 0, 0, or infinite solutions. And I could ask you in this case, what would those infinite solutions look like? It would be 3 planes intersecting in a line that went through 0, 0, 0. Okay? All right, number 4, solve the following system. At the conclusion of your work, state whether there is a unique, no, or infinite solutions in the event of infinite, etc., etc. Okay, so the first thing I look at here, okay, if I look at the system to begin with, before I even press forward, I want to just assess it. Notice no row is a multiple of the other, okay? And there are 4 equations, 5 unknowns. I know for a fact there will be infinite solutions. Now, this is what I was talking to Heather and Layla and I forget, I think Robbie and was it I forgot, someone else. In the process of trying to put this into reduced echelon form, okay, you can pause me if you want to, and notice here, your row moves may be different than mine. I also, because this is an explanation screencast, I did more steps than I necessarily needed to, and for some reason it's not letting me show the entire thing here. Let's see if I can widen this screen a little bit. Oop, I can't. Okay, I'll do this then. How about that? Okay. But something happened on my 3rd move. I noticed this, right? And I think I was talking to Connor, right? This happened to you, Connor. But what's interesting here is, look, in the course of me trying to get reduced echelon form, look what happened. Whoa, it skipped a column. It went 1, skip 1, right? And that may happen. And when that happens, we like that. That actually makes our life a little bit easier, okay? And I was saying to Heather, too, she said, like, how do I know that's going to happen? And here's the answer. It's not very sophisticated. It will just happen. Like, in the course of you trying to rewrite an augmented matrix in reduced echelon form, it will just happen. If that is what the matrix is fundamentally going to simplify to, it will happen of its own accord, okay? Assuming you didn't make a careless mistake. But here, look what I did here, okay? I think it was At this point, what did I do next? I cleared this -2. I made it a 0 down here, okay? And here are my leading ones. Look, leading 1, jump position, leading 1, row of zeros. Now, what I'm going to do now is, just because it's easy to do, I'm just going to clear any of the spots above my leading 1. So this is already 0. I'm going to make this a 0. I'm going to make this a 0 here. And that's my next few moves down here. You see that? Okay, and my next few moves down here, and here is what I've gotten. All right, now this, in terms of reducing your augmented matrix, this is the best you can do. The best you can do. The best you can do. Leading ones are in as close as diagonal as possible. Love the row of zeros. That always makes my life easier. Wherever I have leading ones, I have zeros below and zeros above. That will make life much easier when I, look at my next step here, take care of, look at the red only, everyone. The red equation comes from the first row here. Second red equation comes from the second row. And the third red equation, okay? Now look at my blue circles. What I'm noticing about this is that all 3 equations have an x sub 5 in them, okay? In other words, for all 3 equations, I can conceive of the other variables being dependent, at least in part, on x sub 5. So I'm setting a parameter. I'm saying let x sub 5 equal t, okay? And if I let x sub 5 equal t, look what happens here. If x sub 5 equals t, my second and third red equation right here, look what happens. That tells me x sub 4 would equal -4 minus 3t. X sub 3 would equal 2 plus t. That's nice. The top equation, I say, oh no, I have x sub 1 and x sub 2 and x sub 5. So follow my arrow, look what I did. This just said, I said, that means x sub 1 minus 2x sub 2 equals 3 minus 2t. I put the t in for x sub 5, right? And then I notice here that when I solve for either x sub 1 or x sub 2, either one, I have to incorporate yet another parameter, because x sub 2 is also a free variable, or what you call a parameter. So I said, okay, well, x sub 1 will equal 3 minus 2t plus 2x sub 2. I said, okay, let x sub 2 be some number u. Okay, so x sub 5 and x sub 2 are the 2 parameters, or they're my 2 free variables. Then I have x sub 1 equals 3 minus 2t plus 2u. Okay, what I said here was, if there's infinite solutions, I would like you to provide me 3 possible solutions. So 3 possible solutions. I just noticed I haven't done that, but let's do it now. 3 possible solutions. I'll just do one, okay? I can let t and u be any number, all right? So one possible solution would be the following. I can let t and u be anything. All right, it's going to be an ordered 5 tuple. Okay, this is not an ordered pair, not an ordered triple, it's an ordered 5 tuple. Yes, it's called a 5 tuple. Let's let x sub 5 be 1. Let's let x sub 2 be 1. There's no restrictions on x sub 2 and x sub 5. So that means, let's see, x sub 3 would be 2 plus 3. X sub 4 would be -4 minus 3, or -7. And x sub 1 would be 3 minus 2 plus 2, or 3. Right? Is that right? 3 minus 2 plus 2? Yes. Here's one possible solution. How do you find 2 other solutions? Again, generate any value for u or t and then substitute. Okay? Very good. Number 5, find 3 numbers whose sum is 34 when the sum of the first and second is 7, and the sum of the second and third is 22. All right. This is actually a fairly simple one. I said let A, B, and C be the 3 numbers I'm looking for. Here, the sum of the 3 is 34. Here, the sum of the first 2 is 7. Here, the sum of the last 2 is 22. And then all I did here was create what is this called right here? This is called a matrix equation. Matrix equation, right? Not an augmented matrix, it's a matrix equation. And what I said here is use your calc. Create this matrix A, create this matrix B, and then the solution is going to be the inverse of A times this b. And I said use calc. I don't have a calc on right now. We just do enter. Okay. Number 6. Okay, Jeannie and Nick. See if there's something weird that happened in your work. But then I did see, I mean, you were very, very careful, Jeannie. So I don't know, maybe I made something silly happen. But here's number 6. Here's how I worked it through. Okay, so number 6 looks like this. It says, I said, this is matrix A, here's matrix B, and I want to find all the possible matrices B such that the product AB equals BA. In other words, I want to find all the possible matrices B so that A and B commute multiplicatively. Okay, so the left hand of this yellow squiggle shows A times B, and here is my A times B. Do you agree? Now that I did this, Jeannie and Nick, I'm going to double check my math. A plus 2C, yes. B, this right here, this entry right here is B plus 2D, yes. This entry right here is 3A plus 4C, yes. This one here is 3B plus 4D. Yes, check. Okay. B times A, BA. Okay, this is A plus 3B. Yes. This one here is C plus 3. Check. This one here is 2A. Check. And this one here is 2, please. Okay, yes, check. All right. Jeannie and Nick, are you looking also? I'm going to make sure I didn't do the Eric Hahn. Eric, are my B's all supposed to be B's, or does some of my D's become B's? Let me see, hang on. D's, B's, D's and B's. Okay. Uh-oh. Is this B? Is this supposed to be a B? Let me see. Nope. 2A plus 4. Yep. Okay. All right. I set all 4 pieces equal. A plus 2C equals A plus 3B. Check. B plus 2D equals 2A plus 4B. Okay. 3A plus 4C equals C plus 3D. 3B plus 4D equals 2C. Okay, check. Just like you, do you see how equation 1 and equation 4 are the same? So then I took equation 2 and 3 in orange. Look what I did. Equation 2 was B plus 2D equals 2A plus 4B, right? Or 2D equals 2A plus 3B, right? Or D equals A plus 3 halves B. Okay, agreed? I agree. Here's equation 3. 3A plus 4C. I just put it in 3 halves B, 4C. So 3A, and the reason why is because if I look at equation 2 and equation 3, there is a way that I could reduce the number of variables between equation 2 and equation 3. Okay, 3A plus 4 times 3 halves B equals 3 halves B plus 3D, right? Which becomes 3A plus 6B equals 3 halves B plus 3D, correct? Which becomes, over here, check over here, 3D equals 3A minus 9 halves B. Okay, so Nick and Jeannie, somewhere, right here, I think my equations are differing from yours. So something is happening. Something's up. Like, look at your work, because I don't remember seeing some of these numbers on when I was looking at your pencil work. What I then did was I solved this equation for D, right? And then I did, oh, right, I solved this equation for D, this equation for D, which equals A plus 3 halves B, okay? And then I put A plus, I think this was just, I came back to it later, it looks like. Yeah, so then, okay, so D equals A plus 3 halves B. I put this equation, what number equation was this? This is me putting equation 2 into equation 3 by substitution. And I get 3 times A plus 3 halves B equals 3A minus 9 halves B. Yeah? And then this is just me solving, follow, follow, follow. So then I get 3a equal da-da-da. The 3a's cancel. I have 9 halves b equals negative 9 halves b, right? Or 18 halves b equals, so b equals 0 and c equals 0. Yeah, this is all kind of, didn't this work on your paper? Why couldn't I find it, Jeannie and Nick? Did you find it? Send me an email because I want to know what happened. Okay, so b equals 0 and c equals 0. If b equals 0 and c equals 0, that's when I went back up to here. If b equals 0 and c equals 0, so look over here. So I wrote, this equation, this was equation 3. It became d equals a plus 3 halves b, but 3 halves b is just c. So if d equals a plus c and c is 0, that means d has to equal a. Which means B, which has the form A, B, C, D, must be a matrix where B and C are 0, and A and D have to be the same. So B must look like this. A could be any number, but they have to be the same, and these have to be zeros, okay? One of the things I think that I will admit right now too is that when I'm looking at your work and you go about it differently, like for Jeannie and Nick and Eric, you go about it differently, and what happens is sometimes like you lose some minor algebra error or like a minor negative somewhere, and when you're mired in this, your eye doesn't catch it. So Nick and Jeannie and Eric, can you catch it? Like I catch either yours or frankly, did I catch somewhere? I want to say I don't think I did, because that is actually the result. Like that is the right answer. So I wonder if you like lost a denominator somewhere. I don't know. But I'm curious now. All right, 7, it says, prove that for any square matrix A plus its transpose must be symmetric. And I gave a very thorough explanation. I said, first, given this question, A has to be square. The reason why A has to be square is because in order for me to add A and the transpose of A, they have to have the same dimensions. You can't add two matrices that have different dimensions. So that's the first thing I did. And then I said, let A equal this general matrix. And then I found the general transpose. And what I noticed is that when you transpose a square matrix, look at my yellow, the diagonal stays the same. The other thing I noticed is that when you transpose a matrix, a square matrix, what happens is, look at my red arrows, you get diagonal position swaps. In other words, you get entries reflect themselves over the diagonal. That's my example of B and D. And when that happens and you add A and plus its transpose, this is the pattern you get right here. Okay, so I said, note that for square matrices, A and the transpose have the same diagonal. Also, if A is square, A transpose has the effect of reflecting terms over the diagonal. I said, see red above. So by necessity, A plus its transpose will be symmetric. Okay? All right, number 8. Here's number 8. 8, it says, for what value of little a is the matrix capital A invertible if A is right here? Okay? Whoops, hold on. Someone just came in the office looking for me, and I don't want to get distracted because I just don't. Okay, hold on. Okay, hi, I'm back. So actually it was a colleague who came to look for me, and there was a meeting, I guess, that I missed. So, funny story, not only did I forget to miss your class, I then came up to the office and forgot about a meeting that I was supposed to go to. So, but don't ever do this, but while I was in the meeting, I pretended to be taking notes on the meeting, but in fact, what I did was a solution over here. But you should never do that. That's very, very rude. Okay, here's what I did. Did I leave off here? Okay, so here's matrix A. I set up a comparative matrix in red. The goal is to get the identity I on this side. And here's just some of my work. Okay, some of my work right here. Some of my work here. Okay, setting up my identity. And I mean, actually, I could have stopped here really and just assessed and saw what was happening, but I decided to go ahead and clear out what I clear out the 0 here. Okay, and I could, if I wanted to, clear out these zeros here. All right, but at this point, it's very clear to me, and I hope clear to you, that if I go ahead and clear out this 2 and -3, all that will do is introduce into the terms over here on the right-hand side, it will introduce some entries that will have a plus 1 in the denominator. Okay, and again, that was actually evident at this point, frankly, but again, for a solution, I want to be thorough. And I see that matrix A is invertible as long as A does not equal -1, because if A equals -1, you're dividing by 0. Okay, but very importantly, when you're in a class or a meeting, you shouldn't take notes on anything other than what's happening in the class. But okay, number 9. Is there a generalization that you can make about the product of two symmetric matrices? Notice I didn't say there are two identical symmetric matrices. Is there a generalization that can be made about the product of two symmetric matrices? No, there isn't. Sometimes two symmetric matrices will result in a symmetric matrix itself, and sometimes they won't. And this justification, when I was thinking about justifying clearly, this is a one where I think, in all honesty, proving it just by counterexample is most efficient. So here's an example. If I have 1, 0, 0, 1, right, times 1, 0, 0, 1, these are inarguably two symmetric matrices, I get the symmetric matrix 1, 0, 0, 1. Okay. If I have the matrix 2, -3, -3, 5, okay, multiplied by, let's see, -1, 6, 2, 2, the result is going to be, hold on, let me do it. So these two symmetric matrices result in a non-symmetric matrix, okay? I mean, I guess the only generalization you can make about the product of two symmetric matrices is that you get a square matrix, but that's not particularly exciting. So this one is just, the answer is no. All right, number 10 and 11, let's see. Determine the acute angle between. Do I need to do 10 and 11, boys and girls? I mean, I looked at your homework on 10 and 11, or actually I saw your homework on the board for all your vector basics homework. They were all fine. They were all totally fine, like very sound, very simple. Someone email me if you want me to do number 10 and 11. Number 10 and 11, but even as I look at number 10 and 11, they're already boring me. Okay, Jeannie, Nick, let me know what, Jeannie, Nick, Eric, tell me what errant negative symbol did I not pick up when I was looking at your paper? And Severin, don't forget, apps 6 matrix. Okay, who else did I want to get back to? I can't remember. Okay, bye.